Welcome to AI Paper Slop. We summarize the absolute avalanche of machine learning research and, distill it down to the core insights you actually need to know.
No fluff today, we are jumping straight in.
Yeah, exactly. So the paper today is called ABot-3DWorld 0. Subtitle is A Universal World Model to Explore Any 3D Space. It's straight out of the AMP CV Lab at Alibaba Group.
And this one is massive.
It really is. So here is the 60-second TLDR for you, especially if you are out there actively engineering 3D scene generation. You already know the pain of massive hallucinations, right?
Oh, absolutely.
Yeah.
Environments that completely break the second the camera turns around.
Exactly. So this paper solved that view inconsistency problem. It introduces a unified pipeline that takes literally any input. Text, single image, casual video, whatever.
Right, and it turns it into a fully explorable, photorealistic 3D Gaussian Splatting world.
Yep. And they achieve this through what they call a Spatial Generative Primitive, which is basically a panorama and point cloud tuple. They pair that with an Agentic trajectory planner and a massive 14 billion parameter panoramic video generator,
Which they post-train with a really brilliant 3D reinforcement learning optical flow reward.
which we will definitely get into. And then they finish the whole thing off with an iterative FLUX-based repair engine. The result is just flawless interactive 3D environments.
It's honestly a masterclass.
Yeah, so if you've been struggling to combine generative diffusion with hard geometric priors without your world warping into, like, a surrealist nightmare class is in session, let's unpack this pipeline.
Well, what Alibaba has done here is they looked at the entire life cycle of 3D generation, starting right from the data itself.
Right.
And they systematically eliminated the bottlenecks that cause those hallucinatory warped spaces we're all so used to seeing.
Yeah, and before we even get into the sexy generative stuff, we have to talk about how they trained this thing, because it solves what I like to call the rig in the shot problem.
That's a great way to put it. The fundamental issue with training a panoramic video model is that you need high-quality panoramic video.
Right.
But think about how physical 360-degree footage is captured in the real world. You immediately run into physical limitations. You have a massive camera rig, maybe a tripod, or a person holding it.
And because it captures 360 degrees, that operator or the equipment is unavoidably in the shot, which actively corrupts the geometry of the scene.
Exactly. You also have uncontrollable camera shake. But most importantly, physical capture lacks perfect 3D geometric ground truth.
Right. You don't get mathematically perfect depth maps or point clouds from just some arbitrary outdoor internet video.
Which means researchers usually have to rely on noisy, monocular pseudo-labels. You basically force a secondary model to guess the depth from single 2D frames.
Which introduces a massive amount of noise before you even start training. You literally cannot hide from a 360 camera. So their solution to getting clean data is honestly a bit like The Matrix.
The Matrix.
Yeah, like instead of sending people out to film the messy, unpredictable real world to train their AI, they basically built a mathematically sound simulation first and then filmed that.
Ah, I see. That analogy actually holds up perfectly. They built this massive virtual world asset bank.
Right.
To do this, they fused proprietary indoor and outdoor captures from AMAP, which is Alibaba's mapping service, with aerial cityscapes, open source data sets like Matterport 3D, and even bootstrapped internet clips.
Which they meticulously reconstructed, right?
Exactly. They baked all of this incredibly diverse data into high-quality, static 3D Gaussian splatting scenes.
And once they had these perfect static 3D scenes just sitting in their virtual engine,
They deployed a virtual panoramic camera to render 81-frame videos along completely collision-free trajectories through those scenes.
that is so smart. Because the recording is happening inside a virtual engine, they can extract perfectly aligned RGB pixel data, flawless depth maps, and exact point cloud visibility masks at every single frame.
Exactly. There is zero camera shake, there is no operator in the shot, and the geometric alignment is mathematically unquestionable.
Which is brilliant for getting clean ground truth. But I have to push back here a little on behalf of the engineers listening. We've all seen models overfit to synthetic data.
Sure.
Does training a model purely on synthetic renders hurt its ability to handle messy, real-world inference later? Like, does it just learn to generate things that look like a slightly janky video game?
It's a fair question. That really is the downfall of many synthetic-only datasets. But the crucial difference here is the origin of the base assets.
Right, because they aren't generated.
Exactly. The 3D scenes themselves are derived directly from real-world captures. They aren't low-poly video game assets modeled by a designer in Blender.
Right.
They are photorealistic reconstructions of actual streets, actual aerial cityscapes, and actual living rooms.
So the visual distribution inherently matches the real world.
You get the photorealism of real observed data paired with the geometric perfection of synthetic extraction.
Okay, that makes sense. So we have this pristine data engine training the system in the background. Now let's talk about what happens at inference time when a user actually hands this model something messy.
Right, the real-world application.
Yeah. This brings us to the core of the architecture.
Yeah.
The SGP, or Spatial Generative Primitive. I was trying to think of how to visualize this for you guys, and it feels like the SGP is kind of the ultimate real estate listing.
I like that. The SGP really is incredibly elegant in how it packages information.
Right, because think about it. When you look at a house online, you want a 360-degree photo to understand the vibes, the lighting, the textures of the room.
Yeah.
But you also want a rough floor plan to understand the structural reality, like where the walls actually are. The SGP is exactly that. It's a compact tuple consisting of high-quality panorama and a spatial point cloud.
Exactly. The panorama supplies the comprehensive 360-degree visual appearance, and the point cloud encodes the hard metric geometry.
And how the SGP acts as a universal translator for any input modality is just fascinating to me.
It really is. Whether you feed the system a text prompt, a single image, a multi-view set of photos, or just casual video, it all gets converted into this one canonical SGP format.
But how it gets there depends on what you feed it,
Yeah.
right? So if you give it rich inputs, like a video of your living room, it relies on rigorous geometry.
Specifically, it uses structure from motion to lift that video into an SGP.
Right. Let's clarify that for a second. Structure from motion, or SFM, means it looks at how objects shift across the frames as the camera moves and uses that parallax to mathematically calculate their 3D depth.
Which means it faithfully mirrors the real scene to minimize hallucination.
Exactly. But conversely, if you give it sparse inputs like a single image or just a text prompt saying, cyberpunk alleyway, it goes down a generative route.
Right, because there's no geometry to extract. So it employs a diffusion transformer, a DIT-based panorama generator they call Panogen, and combines it with monocular geometry estimation to generate the SGP from scratch.
This bifurcated routing is so important because I know what some of you are thinking. Other models out there like Marble or HY-World 2.0, they also take multimodal inputs.
They do.
They let you input a video or an image. What makes this SGP approach fundamentally different from what the competitors are doing?
The main distinction lies in how they respect the source material. Competing systems often handle rich inputs, like a video, by collapsing them through a cascade of generative models. They might run a video-to-text model to describe the scene and then feed that text description into a text-to-panorama model.
Oh, wow.
Yeah, and when you design a pipeline that way, you are actively throwing away the hard geometric evidence that was present in the original video.
You're forcing the AI to play a game of telephone with itself, which just massively amplifies hallucinations.
Exactly. The resulting scene might look pretty, but it diverges completely from the original input.
So you upload a video of your kitchen, and it generates a kitchen, but it's completely forgotten the layout of your actual kitchen.
Precisely. The SGP's rigorous geometry route anchors the output directly to the observed reality. If the pixel data is there, the model is forced to use it.
And if the data is missing, like with a text prompt only, then is it allowed to hallucinate?
Exactly.
Okay, so we now have our canonical SGP, we have our 360-degree vibe, and our point cloud floor plan. How do we actually explore this space to build out the rest of the world?
Well, the system utilizes a geometry-grounded agentic planner, and this evaluates the navigability of the SGP's point cloud.
So it isn't just randomly panning a camera around.
No, not at all. It calculates collision-free paths using 3 highly context-aware strategies.
Right, the first being spatial coverage, which makes sense. You need to look behind the couch to know what's there, actively maximizing parallax so the downstream reconstruction gets the best possible angles of occluded corners.
That's the baseline, yes.
But how does it handle unstructured narrow spaces where a random camera move would just, crash into a wall?
That's where the second strategy, autonomous roaming, kicks in. It dynamically adapts the trajectory based on the density of the point cloud.
Oh, okay.
This ensures the camera path naturally funnels down tight corridors without clipping through the geometry.
And the third strategy is where the model starts acting almost human. Semantic engagement.
Yes. It actually employs a vision language model to actively identify salient objects in the scene.
So if it spots a bookshelf or display case in the point cloud, the agent effectively says, hey, that object looks semantically dense. Let's walk over there and get a closer look.
Exactly. This ensures that the generated video captures high-fidelity details of the most important objects in the room, rather than just wasting generation time staring at an empty white wall.
Makes total sense.
And once this trajectory is planned, it's fed into the panoramic video generator. This is a massive 14 billion parameter model built on the VCE architecture.
Which is a really robust video generation framework.
It is, and it takes the dense point cloud as conditioning.
Now, 14 billion parameters is a heavy piece of machinery. But for the ML engineers listening, there are two massive technical details here that we need to highlight about how they pull this off.
Right.
First is how they solve the panorama wraparound problem. Because if you've ever trained a model to generate a 360 image, you know the dreaded seam artifact, right? Where the left side of the image doesn't perfectly align with the right side.
It's a classic limitation of standard convolution and attention mechanisms. The neural network only looks at local patches of pixels.
Right.
So when it looks at the far left edge, it doesn't natively understand that it's supposed to be touching the far right edge. ABot solves this during the denoising process with something called latent uniform shift.
Also known as circular padding, right? I had to read this section twice because the solution is just so elegant.
It really is.
Imagine you are painting a picture on a rolling cylinder. Normally, diffusion models paint the flat image and just hope the edges line up. But here, at every single denoising step, they physically roll the latent tensor along the width dimension.
They constantly move where the seam is located during the diffusion process.
Yeah. By the time it's done, the edges have been blended from so many different angles that the scene literally cannot form.
It forces the model to maintain perfect boundary continuity no matter where the camera's looking.
It's brilliant.
And the second major technical detail is acceleration, because a 14B parameter video model running 50 full diffusion steps per frame would be agonizingly slow for practical use.
Oh, completely unusable.
To solve this, they apply light X2V style step distillation. They successfully compress the sampler from 50 steps down to just 4 steps.
Which is huge for usability. It brings the inference time down to about 12 minutes on a single node of 4090 GPUs. That's borderline consumer hardware, or at least prosumer.
Exactly. Okay. So now the model has output a beautiful, rapidly generated 360-degree video. But how do we enforce the laws of physics on those pixels?
Right, because 2D diffusion models are notoriously bad at cross-view 3D consistency. Object permanence behind you morphs into a potted plant.
That is exactly where 3D reinforcement learning, or 3DRL, comes into play. They implement a post-training stage based on policy optimization to strictly enforce physics.
And they achieve this using optical flow. Let's think of optical flow as a digital breadcrumb trail.
Okay, I like that.
It physically measures pixel displacement vectors across frames. So if you pick a pixel on a coffee cup in frame 1 and the camera moves forward to frame 4, you can track where that pixel moved.
Yeah.
That's your forward flow.
Right.
Now, if you calculate the pass backward from frame 4 to frame 1, that pixel should land on the exact same coordinate it started on. If it doesn't, it means the model hallucinated the physics and the cup morphed or shifted in an impossible way.
That forward-backward cycle consistency is the absolute core of the reward function. It actively punishes the model if the breadcrumb trail breaks.
Right.
But there is a severe computational catch here. You cannot easily run an optical flow algorithm on a warped equirectangular panorama.
Because of the polar distortion, right. At the top and bottom of a 360 image, it stretches the pixels so severely that it breaks the flow calculations.
Exactly. So instead of using the full panorama, they sample perspective pinhole crops along the equator of the image.
So they just extract flat, normal-looking, undistorted video crops.
Yes. And then they use a specialized tool called RAFT to estimate the optical flow between frames with a temporal stride.
Which brings up a question I had while reading this.
Mhm.
If we want perfect 3D consistency, why not just force the model to build a full 3D mesh at every training step and check the geometry directly? Like, why bother with this 2D pinhole cropping workaround?
Because rendering an explicit 3D mesh, checking its topological coherence, and then backpropagating through that volume at every single step of a reinforcement learning loop,
That would be way too heavy.
it would be computationally catastrophic. It would grind the training to an absolute halt.
Oh, yeah.
The optical flow cycle consistency is a brilliant lightweight proxy. It enforces 3D coherence natively in the 2D pixel space without ever having to construct the explicit 3D volume during the reward loop.
Wow, so it's a massive shortcut that gets you 90% of the way there.
Yeah.
And they also include a fidelity reward using LPIPS, which essentially measures how perceptually similar two images look to the human eye, right?
Yes, the LPIPS reward is essential. Because if you only reward a reinforcement learning model for optical flow consistency, it will quickly figure out a way to cheat the system.
Reward hacking.
Always. The absolute easiest way for a video model to achieve perfect pixel tracking is to generate a completely static video where nothing moves, the camera sits still, and the scene is just a blank wall.
Of course. So the LPIPS fidelity reward acts as a counterbalance.
Exactly. It measures perceptual similarity to force the model to stay true to the original generative distribution, ensuring it actually explores the complex space while maintaining that physics-based breadcrumb trail.
Incredible. So we now have a mathematically coherent 360-degree panoramic video that strictly obeys the laws of physics. But a video is still just a video.
Right.
The final step is baking this into a permanent, explorable 3D Gaussian splatting asset that a user can actually walk around in.
And that takes us to the final stage, the ABot-3DWorld reconstruction and repair engine.
Okay, how does that work?
The pipeline takes the planned trajectory from earlier and a sparse point cloud generated via structure from motion on the newly generated video. It uses those to initialize a vanilla 3DGS optimization.
But because the video was generated by a diffusion model, it's inherently going to have some low-resolution areas or slight artifacts, right? Diffusion is amazing, but it's never perfect.
Oh, definitely not. You'll always have a slightly stretched texture on a wall or a chair leg that looks a bit melted. To combat this, they introduce a FLUX-based iterative repair loop.
Okay.
The system actively renders novel side-views from the coarse 3DGS reconstruction. It then uses an image-to-image FLUX model to super-resolve the textures and fix those inconsistencies.
Wow.
It takes these newly repaired, high-res images and feeds them right back into the 3DGS training loop to refine the physical geometry.
It's like having a digital artisan walking around the 3D space, taking photos of the ugly parts, painting over them to look perfect, and just pasting them back onto the world.
That's a great way to visualize it.
But I have to ask about the absolute kryptonite of 3D Gaussian splatting.
Which is?
Highly reflective surfaces like water or glass, and dynamic moving objects. Like if the video has a pond reflecting the sky, Gaussian splatting usually freaks out. How does ABot survive that?
Well, standard 3DGS densifies, meaning it adds more geometric points based on screen space gradients. If a pixel is hard to render, the gradient spikes, and the system throws more Gaussians at it.
Right. And a mirror or a water surface constantly changes color depending on the viewing angle. The model interprets that view-dependent color shift as missing geometry, which causes continuous gradient spikes.
Exactly.
The system panics and spawns thousands of Gaussians above the water, trying to build the reflection in midair as a physical object, leaving you with floating clouds of garbage.
It's a huge problem. But to solve this, they replace that deterministic twirl with MCMC, or Markov chain Monte Carlo, opacity-weighted probabilistic sampling.
Okay, that is a mouthful.
It is. But basically, by decoupling the density control from those gradient triggers, the model uses stochastic sampling.
Right.
It allows inefficient or erroneous Gaussians over the water to literally fade out and die, rather than endlessly multiplying in a runaway chain reaction.
Okay, that is incredibly smart. And what about moving objects? Say the input video had a dog walking through the shot.
Dynamic objects violate the static scene assumption of 3DGS. That is handled by transient suppression.
Okay, how does that work?
They use a combination of 2D semantic masks and a learnable 3D mask scaler attached to each individual Gaussian. If a primitive is inconsistent across multiple views because the dog physically moved from frame 1 to frame 10, it gets identified and seamlessly pruned from the final geometry.
So it basically acts as an automated cleanup crew, ensuring you are left with a pristine, static 3D world.
Exactly.
And this isn't just some abstract academic exercise, right? Because the outputs of this pipeline share a metric frame and run in real time, Alibaba is already pointing this toward actual product applications.
Yes, the most prominent being what they call portal time travel.
Which sounds so cool.
It really is. Because the generated 3D worlds are perfectly scaled and metrically aligned to the original SGP, you can use a simple screen space mask to transition between them.
It's like augmented reality on steroids. You could be walking down a 3D reconstruction of a modern street, step through a digital portal, and seamlessly walk into a historically reconstructed generative version of that exact same street from 500 years ago.
Right. No loading screens, no mismatched scales, just the mathematically perfect transition.
That is wild.
And the portal effect is a powerful demonstration of why maintaining rigorous geometric priors is so vital. If the generated world wasn't metrically constrained by the SGP and the 3DRL optical flow,
That portal transition would instantly break due to spatial misalignment.
exactly.
Which leaves us with a really provocative question to think about. As the industry moves from just generating isolated 3D objects to generating entire explorable scenes, if we can reliably distill physical cycle consistency into 2D diffusion models using reinforcement learning and then lock it down with geometric post-training like 3DGS, do we even need native 3D diffusion architectures in the future?
It's a massive question.
Right, like will these highly optimized 2D video models forced to obey the laws of physics simply win the race to build the metaverse? It's definitely something to chew on as you look at your own pipelines. Thank you for tuning in to AI Paper Swap. We'll catch you on the next one.